Hello, my name is Carrie Lingle, and I'm a Global Customer Education Manager at Neogen. It's my pleasure to speak to you all today on global market trends and the importance of improving productivity in the food industry. During my presentation today, I will review current food safety megatrends from a recent survey conducted by Neogen, the impact of pathogen test methods as they relate to the megatrends, considerations for implementation of a pathogen method, and best practices for capturing and interpreting pathogen data to increase productivity. And so let's begin today's presentation with some current food safety megatrends. In 2022, Neogen commissioned a megatrend survey reaching out to 75 global participants in all areas of the food supply chain. And the outcome of the survey was an analysis which identified the top 6 megatrends affecting the food industry. For my presentation today, I'll focus on food contaminants, automation, labor and talent, and the opportunities to improve productivity to help overcome challenges associated with these megatrends. So the first megatrend I identified was food contaminants. A food contaminant can be any biological, chemical, or physical component that is introduced to a food source due to naturally occurring sources in the environment from which the food is harvested, or artificially introduced through processing. There were 2 prevailing themes that were noted throughout the survey relating to food contaminants. The first was changing landscapes. One example of this is the climate change. So weather patterns have been constantly evolving due to global change in climate. And the participants of the survey noted that such changes will elicit new and evolving mycotoxins and pathogens in the raw food supply that will need to be regulated and tested for to ensure that food is safe for consumers in the future. There's also the emergence or the potential emergence of resistant strains. So use of antimicrobials, antibiotics, and sanitizers could lead to new strains of microorganisms, which are hazardous to human health and resistant to all current lines of defense and detection. And then finally, amongst the changing landscape, there also are some regulatory changes. There are increasing regulatory standards, which drive the need for testing to be faster, easier, and automated. The second key theme were changing lifestyles. We can see in the market there are novel food ingredients due to an increase in vegan and vegetarian diets, which are driving a demand for plant-based replacements for meat and cheese. Robust testing methods for pathogen and spoilage organisms for these types of foods will become critical in the future. And introduction of new ingredients and food types will lead to more challenging matrices for the test methods, which are used to make sure that they are safe. There are also specialty diets. There's a consumer trend or demand for free from and minimally processed foods, which will continue to increase. Testing for allergens, GMOs, antibiotics will become more common and include more targets. Minimally processed foods create a challenge for pathogen control, and some participants from the survey predicted a rise in recalls in these types of foods. And then finally, home delivery. So the COVID pandemic led to a boom in takeout, food delivery services, and make-at-home meals. These types of services are well regulated, and testing to ensure the safety of these products when they're prepared and consumed at home could become a need in the future. The second megatrend is labor and talent, which include the network of organizations, people, and resources involved in delivery of a product to a consumer. With labor shortages and turnovers at high rates, ease of use and highly automated platforms ranked high on the list of needs in the food safety industry. Use of automation in data collection, analysis, and storage would greatly increase transparency throughout the entire supply chain. Essentially, the themes that are seen in this megatrend have a potential negative effect or some consequences on the productivity of the overall food operation and desired food safety goals. Finally, automation. Automation describes a wide range of technologies which reduce human intervention in processes. As mentioned in the previous megatrend, many producers and processors face major labor challenges, making the need for automation more important. Any kind of technology that takes user error out, produces quicker results and results in less hands-on time is desirable. In other words, automation is one key tactic to improve productivity, which may be affected by labor and talent shortages. Of course, there are many activities which make up a food safety program to help reduce the risk of food contaminants. And one activity is the test for biological food contaminants, also known as pathogens, in raw materials, the processing environment, and finished product. When considering opportunities to increase productivity in a food operation, often the laboratory which conducts these pathogen tests is overlooked. So I'd like to review the importance of productivity in the laboratory and consider ways in which the food testing laboratory can overcome challenges occurred by the previously mentioned megatrends. So at the heart of any operation in laboratory are the personnel. And a strong and competent group of staff members is really key to enhancing productivity. And there are four main areas which contribute to this. The first being experience and skills. The second, training, cross-training, and external training. So by experience and skills, I mean that the choice of personnel is really important. And when you're choosing a personnel to be in a laboratory, you want to be realistic. It should play a factor in planning. So how you choose that personnel should play a factor in planning for the future of an operation and having succession plans in place to replace individuals who may leave in the future. And then you want to identify who will be doing which tasks and who can cover for them if they're absent, which promotes scheduling flexibility and helps maintain productivity in the lab overall. For training, regardless of the individual's experience and skill level, all new employees should undergo a general and basic training. And these ongoing technical trainings are a really good time to ensure that the staff who are performing the methods perform it in the same way, and that no one has started to drift away from the proficiency of the task since their initial training. Cross-training, so over time, a laboratory will see special projects come in, or they may experience unexpected staffing shortages, which make it difficult to keep up with the demands of routine tasks, thus decreasing the productivity. So ideally, a laboratory would already have plans in place to ensure that they'll be able to keep up with these increased demands. And cross-training of personnel to cover these tasks or responsibility is a really effective way of filling any staffing gaps with minimal effort. It also allows for those individuals to assist with other tasks should they find that they have some extra time on their hands during their shift. And then external training. So you're always going to have some sort of internal training, but for industry best practices or regulatory updates, seeking out external sources for education and training is a really beneficial way to make sure that your staff is trained and educated without putting any sort of extra pressure or demand on the resources that are already limited. All right, so now I'm going to talk a little bit about the laboratory layout and design and how that contributes to the overall productivity. So as stated in ISO 17025, the 2017 version, which is the current version, the facilities and environmental conditions shall be suitable for the laboratory, and they shall not adversely affect the validity of the results. So effectively, this means that the layout of the laboratory needs to be logical for the process flow of the samples coming into the laboratory. This helps to protect the integrity of the test itself. So when evaluating a workflow and how the sample travels, one must think if the step or the activity of the test methods being performed next to each other are compatible. So additionally, we need to consider the proximity of each task to the previous and then next tasks. Sometimes it's worth taking a step back and just watching or mapping the flow of traffic in a laboratory to see where any inefficiencies lie. A great example is when with pathogen testing, in which you don't want to have sample preparation near the confirmation testing of the pathogen, because this could result in cross-contamination. So in this example, we can see that there's actually a physical barrier barrier between the sample preparation area and the incubation area where the pathogen testing is performed. As it relates to the pathogen methods themselves, there can be several factors to consider in which improvements can be made in laboratory productivity. So the first being internal and external requirements. Next is the operational needs, followed by the laboratory's capabilities, and finally considerations for equipment and method automation. So when considering methods, laboratories will want to consider their own internal requirements, which may have an impact on productivity and day-to-day activities. This may include whether the foods which are tested routinely in the laboratory are within the scope of the method's intended use and validation. This may result in special steps or modifications needed for these samples being tested, and if that will increase or decrease the productivity compared to other methods that are out in the market. I'll also talk a little bit more about this in the next section of my presentation. And then there are also external requirements which should be considered. So for example, does the facility's customers or the customers purchasing the food product being tested have a preference on which method is being used? And then when evaluating or examining the methods either currently used in the laboratory, it's also helpful to consider if the personnel have the skills needed to perform the method well and consistently. So perhaps there's an easier method to train and perform, which could improve the lab's current workflow. So here I have an example of a method designed for efficiency. And with the method in this example, there's no mixing of reagents or buffers, as the lysis and reagent tubes come pre-filled and are ready to use. Visual checks are in place to verify that the lysis reaction is complete, and the tools that come with it make it easier to work with one strip at a time to help minimize cross-contamination. In total, it takes 37 minutes of the analyst's time to run the assay. Another area in which a method can affect efficiency is in the area of operations. So does the method allow the facility to respond quickly to issues? Or will a shorter incubation time allow the facility to release product faster and subsequently resolve any storage constraints? And lastly, are there any gains or improvements the methods will bring to root cause investigations? Finally, when choosing equipment or automations, facilities should consider what the return on investment will be and factor in any little nuances. So will the equipment really be efficient? And will there be productivity gains aligned with the cost? Will there be any maintenance costs associated with it? What happens if the equipment is broken? What's the plan? If the lab invests in automation, what will the analysts do with their extra time if this is taking the place of their current activities? So now that we've considered how a pathogen method impacts productivity in the laboratory, what considerations should also be taken when choosing a method? But what are the appropriate steps to take when implementing that method to ensure that it's being conducted correctly? So to start, let's make it clear on what the difference is between validation and verification. These two terms are very often used incorrectly and used interchangeably. Verification will always follow validation. A method is first validated, demonstrating that the method performs equivalent to the reference method based on defined criteria. A laboratory can then choose to use a validated method in their laboratory. Before putting that validated method into routine use, they must first verify or prove that they correctly use the method to achieve those key method criteria. So validation is about the method proving that it works. And verification is about the laboratory proving that they know how to use that validated method. So to begin verification, a laboratory will first need to review the validation data of that method to determine what food categories were included in that validation. Is it a broad range of foods? Is it a limited range? Were there some other categories included? So we talked, for example, about some of those novel food products and megatrends. And do the foods that were tested in those validations apply to those novel foods, for example? And then for each method, you'll conduct 2 stages of verification. So the first type is called implementation verification. And this is conducted first because its purpose is to demonstrate that the user can perform the method correctly. And to demonstrate this, you will use or test one food item. So for qualitative methods, and this is from the ISO 16140 Part 3 2021 standard on method verification. They ask that you choose one food item that was tested during the validation study. And it should be a food item which is a typical food item that's also routinely tested in that laboratory, but it could also be just the food item that was used in the validation study and not tested in the laboratory. You also want to use this food item and the same sample size which was used in the validation study to conduct your implementation verification study. So essentially, you're proving that you know how to run the method because you're going to compare that back to the validation. So you need to use the same food, the same sample size, etc., to say, yes, we can perform it just as well as what was done in the validation. The second type of verification is food item verification, and its purpose is to demonstrate that the laboratory or the user lab is capable of testing the types of food it claims that it tests routinely within the scope of their laboratory application. And because you're not asked to test a lot of food items in verification, that user laboratory is asked to test challenging food items. So the most challenging food items that they routinely test in their laboratories. And these are food items which have properties that could affect the test method, and therefore the outcome of the analysis. So properties such as pH, water activity, microbial inhibitors, which come from spices like garlic and cinnamon, etc. So as I mentioned, a lot of this information is coming from the ISO 16140 Part 3 standard on method verification. I'm going to do a high-level summary of how you verify a pathogen or a qualitative test method. If you want to find out more details on how this process should be conducted, I would refer you back to the standard itself. As I said, I'm not going to go into too much detail here today. So for qualitative methods, the ISO 16140 Part 3 standard asks to determine the estimated limit of detection, or the ELOD, which is the performance characteristic required to be determined for the verification process. The ELOD 50 is the level of detection at the 50% probability of detection. So notice that this is an estimate because the number of samples tested in this verification are too small compared to what's actually required to do an accurate calculation of the LOD 50, which is required by the validation study. In the verification process, the laboratory will first start determining the ELOD 50 for the food item selected for implementation verification. If you go to Table 3 of the standard, we have 3 different protocols to determine the ELOD 50. So Protocol 1 asks for the artificial inoculation of samples at a high, intermediate, and low level. This protocol is used when we utilize a culture without prior knowledge of the exact concentration. Something which is important to consider is that the standard will ask us to know the LOD 50 of the validated method. So if that's not available, Protocol 1 probably isn't a good option. The other option, which may be simpler, is Protocol 3, which is used if there's a reference material that contains Salmonella or the pathogen, or the test target, I should say, in a known concentration. So the protocol will ask me to spike 7 samples with 3 to 5 CFU per test portion. And in this case, you don't need to know the LOD 50 of the validated method. And we can use Protocol 2 if the protocol we did choose did not work well or as expected, and we need to repeat the study. So in this example, I'm going to show an example of the results, and we're going to use Protocol 1 as described in Table 3. And for that, we needed the LOD 50 of the validation study. So as I mentioned, these are our example results following Protocol 1. And we found we got 1 positive in our high inoculation level, 4 positives in the intermediate, and then 2 positives in the low inoculation level. We also found that when verifying the concentration of the inoculum, that there were 13, 4, and 1.4 CFU per mil, which is close to what we needed, so the data so far looks good. But is it acceptable? So to know that, we need to go to table 6 in the ISO standard, and you'll see that there are some tables similar to those from the most probability or most probable number. So in those tables we find here, the ELOD50 for 1 positive at the high inoculation level, 4 positives in the intermediate, and 2 positives in the low inoculation level correspond to a value of 0.7 times the lowest inoculation level. So 0.7 multiplied by the lowest inoculum level in this case is 1.4, which results in a LOD50 of 0.98. But is that good or is that bad? So to find out if it's good or bad, we can go to table 16 of the standard, which defines the acceptability limit. So whether you're using protocol 1 or 2, the ELOD50 should be lower than 4 times the LOD of the validated method. So we got a 0.98, and this is lower than 4 times 1, which was assumed to be the LOD of the validation for our test method that we're verifying. So we passed. So from here, the laboratory will use the same methodology to determine the ELOD50 for food item verification using the challenging food items selected from their routine testing. And once this is completed, the results meet the acceptability criteria. The method is now considered verified. So we're done with implementation verification. We can perform the validated method correctly. And then when you do food item verification, we now know that the method works for the foods that we routinely test in our laboratory. Finally, so we've done all this testing, we have a method that works, and then we're generating all this data. And I think it's important to remember that the laboratory in these food processing facilities aren't just running tests and saying yes or no to releasing product. They're really a center for generating useful data, which tells a story. And so if you're one of those people that's generating all of this data, you need to stop and consider, is this data, are you working to just create this data, or is the data actually working for you and helping you and your processes and making the food safer by reducing the risk? So we covered in the first half of this graphic, making our laboratory processes more efficient as we collect samples, record the results, and transfer data to a repository. But why just stop at this point? Analyzing and visualizing and taking action with the data enables continuous process improvements. And there are a variety of ways in which you can visualize data. So whether they're qualitative results or quantitative results will probably help dictate how you graph or you lay out the information. But these are just some examples. So here we can see a visualization of data over space. So these are yeast and mold counts from the air or over various lines. And so we can see which of the processing lines is more likely or more prone to having yeast or mold contamination from the air. And we can decide maybe we need to put in some mitigation steps because this is not acceptable for the foods processed on that line, or maybe we need to process different foods on this line because we're having a hard time controlling yeast and mold, for example. Another example here is visualizing results over space. So here we have a map of a facility, and we can highlight where we're finding positives in our pathogen testing, for example, and how frequently those are occurring, where our hotspots are, where we need to make sure that these pathogens are not traveling to, how are we keeping them from getting from one room to the next, for example. Another example I have here is visualizing data by object type. So in an environmental monitoring plan, you're swabbing various pieces of equipment or locations in the facility. And it may be helpful to consider which areas are more prone to having, in this case, we have lactic acid bacteria counts. And some of the information this might tell us is maybe our spoilage or pathogen contamination is coming from a particular location, or maybe that particular part needs to be replaced or have preventative maintenance routine or performed on it more routinely than we're currently doing. And one way that we can maybe automate and become more efficient with our data analysis is using an analytics software which aggregates all of these results into a useful tool and transform that data into action. So in an environmental monitoring program, mapping of pathogens and other hazards within a sample plan enable a facility to identify maybe transient or resident issues. So imagine what information you can glean when you have the data from multiple test types in your environmental monitoring plan put together into one system, bringing those results together so we can see an example here of an analytics program that can help streamline your data entry workflow and generate automated schedules. It's also a great tool for audit support and compliance because all of your corrective actions and your retest results are aggregated appropriately. Helps with documentation of processes to help streamline an auditing process. So here's an example, a case study, if you will, of how automating your data management really increased productivity. So we have a case study from a global dairy products producer, and their customers' auditors had highlighted inconsistent practices as a serious issue for these facilities. So before automating their EMP process, they experienced 6 to 8% of positives with just a low number of tests taken. And after implementing automation of their EMP results, they were able to enable systematic testing and discovery of all positives. So after 6 months, they launched some remediations or mitigation steps, which were tracked and verified. And then within a year, their number of positives began to stabilize and then decline. So in the end, they were able to have better visibility to what was happening in their facility, lower their risk, and use fewer resources for activities such as unplanned cleaning. And of course, management of data in a consistent, efficient manner helps transform the overall food safety culture of a facility by enabling effective sharing of information. And sharing of information helps enable staff to see positive impacts on performance and that goals are being met. It also allows ownership of generating and interpreting an immediate result. Personnel respond well because they can connect with the process. Management can recognize and reward staff and communicate opportunities for improvement. And so on that note, thank you for your time today. I hope you found this presentation useful, and I'm happy to answer any questions that you have.